We have an inductor which has an unknown inductance and a resistor with R equal to 8 kilo ohms connected in series with an ideal battery. So the battery has no internal resistance of 65 volts with that as our circuit. And after 7 milliseconds, so we have a timestamp here, the current is 1.85 milliamps. And so we want to calculate both the unknown inductance, so L, and the energy stored, which we know is 1/2 Li squared. So we know the current, so we'll just need to get L in order to calculate both of these. Now for these types of circuits, right, so RL circuits, we know the following. We know that the current at any time t is the voltage supplied by the battery divided by the resistance of our resistor, and then we have this exponential term which trends towards 1 at large t's. So as t gets large, this term gets small, and this whole thing tends towards 1, and so our current at long periods of time is going to be constant and look like what we would expect for just a resistor connected to a battery. All right, so we need to solve this for L, our unknown. We know T, we know R, and we know our voltage from the battery and our resistance. And we also know our current at some time T. So we're going to do this symbolically. So let's begin. We can do I times R over our voltage is equal to 1 minus e to the minus t over L divided by R. And we're going to try and get this exponential term by itself. And so let's swap sides here. We got minus e to the minus t over LR, L divided by R, is equal to 1 minus I R over epsilon. And you'll notice that this whole term has no units, which it does have to have by definition. We're going to take the natural log of both sides, and so that is going to get me a minus t divided by L divided by R is equal to the natural log of 1 minus this quantity over here. And we want to solve this for L. And so let's begin to get L by itself. L over R is going to be minus t divided by the natural log of the quantity 1 minus IR over epsilon, or over our EMF. And then finally, we can get L by itself. L is minus our product of our time times our resistance over this natural log. And we can plug all our quantities in, right? So we know the resistance, we know the time, and we know the current at that time. And so if you plug everything in, you should get something like 215.4 henries. So that's the first part of our problem here. And the key to this really is remembering how to get rid of exponentials, which is the natural log of e to the x is just x. Okay, so the second part of our problem is calculating the energy. And for that, actually, we can just do it up here. It's going to be 1/2 times the inductance that we just calculated, 215.4 henries, times our current squared, which is 1.85 milliamps. So 1.85 times 10 to the minus 3 amps squared. And you put all that into a calculator, and it's not a whole lot of energy, but it's not nothing. 3.69 times 10 to the minus 4 joules for our energy.